So, very good morning to all of you. So, yesterday we started with Schrödinger's equation, and then we used variable separable approach, and uh, and from one side we had time dependent Schrödinger's equation, and uh, and we obtained an expression for time evolution operator, right? And now we will take the time independent part of Schrödinger's equation. So the left hand side is equal to En, the right hand side is also equal to En. So that's the case. So we'll have to start from here. So this thing must be equal to En, right? So now how I have to move? Don't get it. I'll take on. Okay, so what we have 1 by psi of x, and then minus h bar squared by 2m, then you have d2 by dx2 psi of x plus v of x, and this is equal to what? This is equal to En, right? And we can think of transferring v of x. So this is 1 by psi of x minus h bar squared 2m. Then you have d2 by dx2. Then psi of x equals En minus v of x. And I can transfer this psi of x on the right hand side. So we will have times psi of x. Right? So I can also transfer this 2m on the right hand side. This h bar squared by 2 will also go on the right side. And what should I write now is d2 psi by dx2. Now this psi is exclusively dependent on position only. It does not depend on time. So this will be equal to minus 2m by h bar squared En minus v of x psi of x. Right? So we have d2 psi by dx2 plus 2m by h bar squared En minus v of x, and psi of x equals 0. So this is our Schrödinger's time independent equation. And we can see that this equation is Schrödinger's time independent equation. Right? So we have separated out the time dependent equation from the original equation, because the original equation is a mixture. The wave function is exclusively dependent on position and time. Then what we did, we used the separable approach, and we chose that the wave function is the multiple of a function dependent on time and a function dependent on position. And then we exclusively got Schrödinger's equation in terms of time, and we got Schrödinger's equation in terms of position. Now, as we know that this Schrödinger's time-independent equation, it's a second-order differential equation, right? Exclusively, and we would like to solve a problem. Say we would like to solve the problem of infinite square root problem, right? So, what is infinite square root problem? You have an ideal system in which you have a particle, and this particle has only kinetic energy, right? And this particle is bound between two walls, and these walls are infinitely big. That means it's impossible for the particle to penetrate those walls. So let's use Schrödinger's time-independent equation to solve the problem. The problem of what? Infinite square root problem. Square root problem. So what you have actually, we have done this part actually in modern physics in the previous course, huh? But here we'll take it as a direct extension. So what we have, we choose a one-dimensional system, right? In this one-dimensional system, you have a particle at x equal to 0, at x equal to say a. And your particle has only kinetic energy. The potential energy of this particle is 0. So potential energy of this particle is 0. It has only kinetic energy. And if the particle is at x equal to 0, that means at this point, what will happen to the wave function? Because to have a physically acceptable solution, what you want that this wave function in your problem should be continuous, right? Its derivative should be continuous. And the point number 3 is that this wave function should be square integrable. It should be square integrable. Only then this the problem that you are solving using Schrödinger's equation will give you the acceptable results. So I have this problem now. I would like to write down the Schrödinger's equation for it. So what is that? That is d2 psi by dx2 plus 2m by h bar square e minus. The particle has no potential energy, right? If it has no potential energy, so this is 0, psi equals 0. Okay. So I have d2 psi by dx2 plus k square psi equal to 0. Clear? And this equation has a solution, right? So I can write down its solution as psi is a sine of kx plus b cosine of kx. Where this k is, what is k? This k is basically 2m by h bar square e. Right? We are applying Schrödinger's equation to this particle. This particle is living in an infinite scalar potential. It is impossible for this particle to leave this potential. But inside the barriers, inside these potentials, the particle has only kinetic energy. It doesn't have any potential. That means it's not interacting. There is no interaction of the particle. Are you getting my point? So this is an ideal system. So if you are thinking about the same problem in real system, it will have interactions. It can interact. It can interact with electromagnetic forces. So what we are assuming here is that this particle has no interaction energy. It has no potential energy, right? It has exclusively kinetic energy. It's only having kinetic energy within the domain of this spherical potential. And now what we will do is we will use the boundary conditions. We will use the boundary conditions to solve this problem. So what will be the boundary conditions? We will have the boundary conditions, yeah? So at x is equal to 0, psi is 0. Because the potential is infinite. In future, you will see when you have the finite potential, then there is some probability for the particle. But here we are assuming that the potential is infinite. So there is no question of penetration of the particle. So if there is no question of the penetration of the particle, your wave function at x is equal to exclusively 0. So I'll be using this boundary condition. So using this boundary condition, what I'll get? I'll get 0 is a sine 0 plus b cos 0. And sine 0 is 0. That means b is equal to 0. So the solution that I chose for the differential equation boils down to only sine function here, because I'm applying the boundary conditions, and boundary condition is telling me that you don't need b. B is 0. Clear? So now what will be my wave function? What will be psi? Psi will be a sine of kx. Clear? Okay? So psi is a sine of kx, and your problem is like this. And this is your x is equal to 0, and this is your x is equal to a. Now I would like to calculate a, and we understand that we can calculate a using normalization condition. Clear? So let us apply another boundary condition. What is that? At x is equal to a, what is psi? At x equal to a, psi is again 0. Isn't it? So if psi is 0, that means this 0 is a sine k. Instead of x, I will use a. I'll use a, right? So, but we understand b was what? B was 0. A was not 0. So a is not 0 here. A is not equal to 0. If a is not equal to 0, then what is 0? That is sine ka is equal to 0. Clear? So sine ka equals 0 is simply sine ka equal to sine of n pi, because sine of n pi is equal to 0. So I will write sine of kx is sine of n pi, and this kx will be then n pi, but this is not x, this is a, right? It's ka. So here we have a, and here we have a. Every time I rub the board, I feel as if the ink is sticking on my hands. Okay, so I have got k. What is k then? K is n pi by e. And this will certainly give you the quantization of energy of this particle. Because k is, what is k? K is assumed to be 2m e by h bar square. Right? So instead of k, I will write 2m e by h bar square. So you will have 2m e by h bar square is equal to n pi by a. And from this you will calculate the energy. Now you see, energy has a dependence on n. What is n? N is an integral number, and this integral number can go to infinity. So there are a range of possibilities, but all of these possibilities in terms of energy are quantized. You will have some specific values of energy for this particle in this infinite square wave. What we expect classically, we expect that this particle will have all energies. It will have all possible energies. But here's a contradiction. The contradiction is that E is what? E is n pi h bar square by twice ma. The point is that your E is dependent on n, and n can be 1, 2, 3, and so on and so forth. So you can have, the particle can have only some specific values of energy. It cannot have all possible values of energy. Clear? Okay. So now let's move on. It's always difficult to move it now. Okay, so where are we? So we want to calculate now. We want to calculate A. We want to calculate A. Because we want the complete wave function. And in order to, how to calculate A can be calculated using the condition of normalization. So we need normalization. We need normalization. And what's normalization? That will be integral if you have psi star psi in one dimension, dx minus infinity to infinity is equal to 1. And we have to use this integral, as I said, to have the physically acceptable solution. The wave function should be square integrable. That is the most important postulate of quantum mechanics. So here I am using the real values of psi. So psi star will be it will be meaningless here. So what will I write here? What's my problem? It goes from 0 to A, right? And for psi star and psi, you have the same thing. What's that? That is A sine of kx times A sine of kx. And then you have dx, and this must be equal to 1. Clear? Okay. So A square will be out. You will have integral from 0 to A. Then you will have sine square n pi by A x. Am I right? Dx is equal to 1. Right? Okay, so instead of k, I have used what? N pi by A. That's why here you are seeing n pi by A. So what's the value of this integral? So this integral will give us, we understand that, we have done it, it will give us A by 2. Right? We have exclusively done it. So this is equal to 1. So what will be A square then? That implies A square will be 2 will go up by A. So what will be A? A will be under root of 2 by A. So this is the value of A which we have calculated using normalization, using the condition of normalization. So I can write down the wave function. I can write down the wave function for my particle. For my particle in this infinite square wave. So what will be my wave function? That will be psi. Now it will be right to write psi n. Because I found that wave function is dependent on n. So wave function will also have n number of values. That means you will have infinite number of values for the wave function in this problem. So psi n will be under root of 2 by a sine n pi by a x. Clear? So I can write down all wave functions. I can write down psi 1. What will be psi 1? That will be under root of 2 by a sine pi by ax. What will be psi 2? That will be under root of 2 by a sine 2 pi by ax. Are you getting? I will get psi 3 equal to under root of 2 by a sine 3 pi by ax. You can explicitly see that you have two types of functions arising here. You are having even function and odd function. The first function is even, the second is odd, the third is even, the fourth is odd. Isn't it? Okay? So if I plot them, if I plot these wave functions, if I plot, say this is my psi 1 of x along x, it's going to give me something like this. And if I plot psi 2 of x, it's going to give me something like this. And if I plot psi 3 of x, it's going to give me what is the difference between the three graphs? Come on. Come on.
Number of nodes.
Number of nodes.
But besides,
So if I assume that these are not nodes, the node is the one where the value of psi is 0. In case of psi 2, I have node 1. In case of psi 3, I will have 2 nodes. In case of psi 4, I'll have 3 nodes. These number of nodes will go on increasing. Clear? What does that mean? Or what does that mean? The point is, what does that mean? I think that means psi 1 is an indication of ground state of my system. Psi 1 of x gives me an information about the ground state of my system. Now as I go to the psi 2, psi 3, psi 4, all of these psis are telling me about the excited state of the system. Clear? Hello? Fine? Ground and excited states. Now, so this is how the wave function behaves. This is how wave function behaves. So what we have, we have even odd functions. This gives birth to orthogonality of the system. Now see, I started from real values. If I have to write down the orthogonality, what does that mean? So that means integral, if I define psi n star psi n dx, they have to be orthogonal. Psi 2 has to be orthogonal to psi 1. Psi 3 has to be orthogonal to psi 2. So what does that mean? That means this must be equal to 0. Right? This must be equal to 0. So if I use it in my problem, okay, so how will I solve it? I have calculated psis. You have psi 1, psi 2, psi 3. So here I can write, I can write what is your limit of integration? It is from 0 to a. Then you have under root of 2 by a sine n pi by a x times the same thing. Okay? I will write the square here. Because I have chosen, in actuality, there has to have, the wave function is actually complex. But here, I have chosen exclusively the simplest problem. And in this problem, I wrote down the solution of Schrödinger's equation in terms of real values, sine and cosine. So, this will be whole square dx equal to 0. So, square of this will give me 2 by a, right? So, I will get, I don't know, I might be doing something wrong. So, here I have 2 by a, integral 0 to a, then you have sine square. Should have, I took what I chose. I chose sine m. So I have done it. So here I shouldn't have taken the square, no? Because I'm using psi m and psi n. So what should I write here? I should write here under root 2 by a whole square will be out. That's clear. So it has to be from 0 to a. That's fine. Then I will write what? Sine m pi by x. Sorry. Sine m pi by a times sine n pi by a. And then you have dx. This is what I want to evaluate. I want to calculate this. Okay? Now you can see here this square and root will go, this 2 will go inside. So this is twice sine theta 1, sine theta 2. And we can write down this. Yeah, come on. So this is 1 by a integral. That is cos of m minus n times pi x minus cos m plus n times pi of x. And then dx from 0 to a. Right? Integrate it. So 1 by a. So integrate it, come on. You will have sine m minus n pi x by m minus n minus sine m plus n pi x by m plus n. So what will be the limit of the integration? It is from 0 to a. So when you will use the limits, the lower limit will give you 0. The upper limit will give you what? Here instead of x you will have a. Here instead of x you will have a. Once you give the limits. Clear? Once you give the limits, you will have a. Now you can see it. What's its value? It is 0. Right? Sine of n pi is 0. Right? So what does that mean? That means you have proved that the wave functions are orthogonal to each other. They are orthogonal to each other. But the question is, if m is equal to n, come on. If m is equal to n, what do you expect from here?
1.
You expect 1. Why? See, if you will apply it here, you will get 0. How do you expect that you will get 1?
It comes to equal to non-linear.
Exactly. Right? So you have both the conditions here. You have two things. One is 0, that tells you orthogonality. Another is 1, that tells you about normalization. So what will you write? It's not going. This is the end of it. This is the end of it. Okay, let me go with the new then. Alright. There's a lot of load on this screen, right? It's not able to bear all those nodes. So what I have integral psi m star psi n dx. This must be delta mn. Well, this delta mn is what? This is called a Kronecker delta function. And for m equal to n, this delta mn is equal to 1. And for m not equal to n, this delta mn is equal to 0. Clear? Clear? Any questions? Come on, I want some questions. Yeah. Come on. No questions? So shall we stop here, huh? Okay, with this, we would like to end this lecture. No.